This presentation is about the use of silanes as reducing agents for carboxylic acids. Alkyl and alkoxysilanes are less sensitive towards hydrolysis and oxidation than boranes or aluminum hydrides, and therefore easier to handle, but are also less reactive. These are some of the most common silanes used in organic synthesis as reducing agents. Some of these compounds are produced on a large scale as intermediates for silicones for the semiconductor industry and for the production of silicon for solar cells. Silanes such as triethoxysilane do not readily react with carboxylic acids and usually require a catalyst to promote the silylation of acids. Also, for the reduction of carbonyl groups by silanes, some kind of catalyst, often a Lewis acid, is required. Unlike reductions with borane or aluminum hydrides, the reduction of carboxylic acids with silanes can be stopped at the aldehyde stage by avoiding an excess of silane. At elevated temperatures or upon photolysis, the silicon-hydrogen bond may also be cleaved homolytically and show a reactivity similar to that of tin hydrides. But in the absence of bright light or radical starters, silanes usually transfer hydride to carbocations by an ionic mechanism, as shown on this slide. Here's a list with some catalysts suitable for the activation and reduction of carbonyl groups by silanes. From an environmental and economic perspective, fluoride salts and zinc or titanium salts are probably the most attractive. This list also illustrates that carboxylic acid derivatives such as amides or esters also undergo reduction in the presence of silanes, and that many procedures can also yield aldehydes or methyl groups, depending on the amount of silane used. The main advantages of silanes is their relative stability toward air and water, what makes them easy to handle and to store. Most silanes are high boiling liquids which can be dosed accurately, and the conditions required for reductions with silanes are quite mild. Unfortunately, a large excess of silane and of catalyst may be required in some instances, though. Because of the danger of over or under reduction, this means that for each substrate, the amount of required silane and catalyst will have to be determined empirically. Then, silanes are capable of reducing a large number of different functional groups and are not always selective. Finally, fires and explosions during large-scale reductions with silanes have been reported, for instance when using triethoxysilane. These were probably caused by silane, a pyrophoric gas which can evolve during such reactions. I'll give you a reference for this on a later slide. This is a typical example of the reduction of a carboxylic acid with a silane. In this case, copper triflate was the catalyst and almost 3 times the theoretically required amount of silane was used. In this example, a smaller excess of the same silane as in the previous example was sufficient to attain a high yield. No hydrogenation of the olefin was observed. The authors also found that when using indium chloride as catalyst instead of indium bromide, the addition of stoichiometric amounts of chlorotrimethylsilane strongly improved the results. Silicon forms strong bonds with oxygen but also with carbon, and the reaction of silanes with complex organic molecules under forcing conditions can trigger a lot of interesting chemistry. One old organic synthesis procedure is the reduction of benzoic acids with trichlorosilane. The first intermediate formed is a benzylsilane, which in the original procedure was then hydrolyzed to a methylarene. There are, however, methods for the conversion of silanes into alcohols, for instance, treatment with hydrogen peroxide and fluoride. I could not find this specific example, but it may be possible to convert the benzylsilane of this procedure into a benzylic alcohol. This sequence would then represent a transition metal-free alternative to the reduction strategies presented on the previous slides. As already mentioned, silanes are not very selective, and a large excess can cause the complete reduction of a carboxylate to a methyl group. Two examples of this reaction are shown on this slide. The second example shows that in these reductions carbocationic intermediates are probably involved, which can undergo intra- or intermolecular Friedel-Crafts alkylation of electron-rich arenes or heteroarenes. The last example on this slide shows that just by decreasing the excess of silane used, the reduction can be effectively stopped at the alcohol stage, even in the case of benzylic alcohols. Here's a list with more recent references for the reduction of carboxylic acids to aldehydes with the aid of silanes. Many of these procedures will probably yield alcohols if the amount of silane is slightly increased. A number of other functional groups can be reduced by silanes. These include olefins and alkynes, and in the presence of palladium, silanes will often release hydrogen, and the reaction will in fact just be a palladium-catalyzed transfer hydrogenation. Amides and nitriles can also be reduced by silanes, and here are some newer examples of such reactions. If the reduction of carboxylic acids is conducted in the presence of primary or secondary amines, reductive alkylation of the amine by the intermediate aldehyde can occur. Certain aromatic carboxylic acids may even undergo reductive decarboxylation and yield unsubstituted arenes or aryl silanes upon treatment with silanes and a suitable catalyst. Also carbon-halogen bonds and even alkoxyarenes can be cleaved by silanes. Such reactions proceed most readily in the presence of palladium or nickel-based catalysts. As already mentioned, the conditions of reductions with silanes are acidic and conducive to the formation of carbocations. These can alkylate electron-rich arenes or heteroarenes, as shown by the example on this slide. The potential formation of self-igniting silane in these reductions was already mentioned. Intermediate carbocations can also react with alcohols, halides or thiols to yield ethers, alkyl halides and thioethers. A procedure was also reported for the direct silane-mediated reductive condensation of nitroarenes with carboxylic acids to yield anylides. Similarly as with boranes, silanes can also bring about the dehydration of amides to yield nitriles. Finally, under certain conditions, carboxylic acids can be converted by silanes into acyl radicals, which can add to alkenes to yield ketones. So, quite a large number of potential side reactions to keep an eye on. Unless one has access to some very inexpensive silane, reduction with borane will probably be easier to optimize and more selective for most starting acids.